In this activity, we'd like to use our Nyquist criteria to analyze the stability of the closed loop system based on a unit feedback system with this open loop plant. And so these steps 1, 2, 3, and 4 help you kind of step through that process. So the first step is to identify how many unstable open loop poles there are. In the second step, we're going to take a look at the Nyquist diagram and count how many counterclockwise encirclements of -1 there are. And then from that, you're going to be able to say whether or not the closed loop system is stable for k is equal to 1. And then I'd like you to generalize that to see if there are values of k that change the number of encirclements and whether or not that should change the stability. So go ahead and give this a shot using the Nyquist criteria and your more recent understanding of the arcs at infinity to analyze this Nyquist diagram. Okay, so I've conveniently written down both the system here and also plotted the root locus. This root locus is automatically telling us the fact that this system is going to be unstable for all values of k. So, but let's go through it as if we didn't know the root locus, which is the idea. In this case, we have no unstable open loop poles. We have 2 poles at 0, and we have 2 poles at -1. When we take a look at the Nyquist diagram, one of the things this is telling us is the fact that this Nyquist diagram is starting at -180. And if we look at the Bode plot, that's particularly clear that this is effectively starting at -180. And that's because we have 2 copies or 2 poles at the origin. So when this is very close to 0, then we have 2 copies of 90 degrees that's pointing directly up to that point. And so for any positive value of frequency along the imaginary axis, we're going to get 2 copies of -90 because of those 2 poles at the origin. Those 2 poles at the origin also create a complete loop or a complete arc at infinity loop. And so that's going to play into how many encirclements we get. What we notice here is the fact that -1 is located somewhere in here, so it's safely nestled within here. And because these these dashed lines start, these are the arcs at infinity, they start without the actual Nyquist diagram from crossing, that means this point -1 is already contained within this kind of sideways U shape that we have here. And so what we're going to do is we're going to trace this out. So this is our direction. So we trace that back. Our arrow points along this way, points back in, and then points back in here. And so if we were to start at the origin and follow these arrows, we notice that along here we make half of an encirclement. We continue to trace, and at this point we've now made a full encirclement. And now we continue to go along, and now we've made another half encirclement and then complete it with another full encirclement. And so that means that we have, again, 2 clockwise encirclements of the point -1, and that's for the gain when the gain is k is equal to 1. If we were to scale this by any number, then increase k, then that means that, or decrease k but keeping it positive, that means that this shape actually, in this case, because this horseshoe shape or this sideways U shape is fixed, it doesn't come back and cross along the real axis. This is going to be fixed across all values of k, and so for that reason, our stability result isn't going to change because the number of encirclements doesn't change as k changes. So our analysis here is going to be the same across all analyses. And in this case, we have no unstable open loop poles, but we do have encirclements. And so that is what leads us to say that it's unstable at k is equal to 1. And the fact that the number of encirclements does not change with k leads us to say that then this system is unstable for all values of k.